So far, we've looked at two-dimensional regions that had areas that could not be found using a formula from geometry. We divided the regions into rectangular strips and approximated the area of each rectangular strip, then added them together to approximate the area of the entire region. In this section, we will be looking at how to find the volumes of three-dimensional shapes that cannot be found using a formula that we know from geometry. We will divide the solid three-dimensional shape into slices and approximate the volume of each cylindrical slice. Then we will add all the volumes of each slice to approximate the total volume of the 3D shape. Before we start, let's remind ourselves what a cylinder is and how we can find the volume of a cylinder. A cylinder consists of all points on line segments that are perpendicular to two parallel regions of the same shape, size, and orientation. These regions are called the bases of the cylinder. Keep in mind that the bases do not have to be circular. To find the volume of a cylinder, we multiply the area of the base by the height of the cylinder. For example, here we have a cylinder. Its base is this shape here. And if I take the area of that, in this case, we're just going to call that area capital A, and I multiply it by the height, then we get the volume of that cylinder. And a lot of times we think that cylinders are required to be in the shape of like a can of soup, but that's typically what we think of when we are talking about circular cylinders. And so the base of a circular cylinder is a circle. The area of a circle is pi r squared, and then we're multiplying that by h, and that gives us the volume of a circular cylinder. Even this thing, this rectangular box, is an example of a cylinder as well. Its base is a rectangle, and the area of a rectangle is length times width, and then we're multiplying it by the height, and that gives us the total volume of this shape. Now let's take a look at a different three-dimensional shape. Let's call this shape S, and I want you to pause and I want you to recognize that this shape looks like a loaf of bread that has been smushed together on the ends of this loaf of bread. And our goal is to find the volume of this loaf of bread. And one way that we can do that is assuming that the loaf of bread was sliced up, I could approximate the volume of this loaf of bread by taking the volumes of each of the slices of bread, adding those together, and that should approximate the overall volume. And so in this first picture here, we have this plane that we're slicing into on our loaf of bread, and this thing is called a cross-section. And if we have it so that our slice of bread is cut somewhere on the ith subinterval, then the thickness of that slice of bread will be called delta x. So delta x is the thickness of our slice of bread. So again, if we cut S into n pieces of equal width delta x, we can approximate the volume of S by adding the volumes of the n pieces. So the volume is approximately equal to this summation. Now, what is it that we're summing? This represents the area of one of the cross sections, and then this represents the width of one of those slices of bread. So basically we're summing the volumes of each of these when we multiply the area times the width. To make our approximation more accurate, we increase the number of slices of bread. So volume, let S be a solid that lies between x equals a and x equals b. If the cross-sectional area of S in the plane P sub x through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is given by v equals the limit as n approaches infinity of our summation from I equals 1 to n of a of x sub I star times delta x, which is basically our definite integral from a to b of a of x times dx. When we use the volume formula v equals the definite integral from a to b of a of x dx, it is important to remember that a of x is the area of a moving cross-section obtained by slicing through x perpendicular to the x-axis. Now, this slice of bread here, it's important to recognize that this is not a cylinder. Now, because it's not a cylinder, that means that a of x is not constant. And the area of each of these cross sections is changing depending on where I make my slice on this loaf of bread. Example 1 says, consider a circular cone of radius 3 and height 5. Part A wants us to find a formula for the linear function y equals f of x that is shown in the picture that goes through the points 0, 3 and 5, 0. So this is talking about this linear function here, and I want an equation for that line, and we know that we can write a line in the form y equals mx plus b, where m is the slope. So slope is rise over run, so to get from each intercept, from the y-intercept I go down 3, and then right 5 units, so that tells us that our slope is negative 3/5, and then we multiply that by x, and then add. Notice that our y-intercept is the point 0, 3, so I'm going to put plus 3 there. So this is the answer for part A. Okay. Part B says, for the representative slice of thickness delta x that is located horizontally at a location x somewhere between x equals 0 and x equals 5, what is the radius of the representative slice? Note that the radius depends on the value of x. So coming back to our picture here, now this seems kind of weird, but pretend that this is a cone-shaped slice of bread. And I have one particular slice of bread here, and I could slice this up at several different places. I can make my cut anywhere between x equals 0 and x equals 5. I just happen to choose some arbitrary place to make my cut in this cone-shaped loaf of bread, where a slice of bread is kind of going to be a circular cylinder. So because this is a circular cylinder, I want to find the radius of that cylinder, and the radius of this cylinder is the distance between the center to the outer edge right here. And really, this is just the y value. So that's what our radius is. Notice that the radius depends on the value of x. So because it's our y value, our radius is equal to negative 3/5 x plus 3. So essentially, part A and part B are tied closely together. Part C says, what is the volume of the representative slice you found in part B? Because this slice of bread right here is a circular cylinder, we know from the previous page that the volume of a circular cylinder is given by the formula pi r squared h, where r is the radius and h is the height. Now, in this case, the height is this dimension here, which is delta x. And our radius, we've already established as negative 3/5 x plus 3. So plugging those into this formula here, we get pi times negative 3/5 x plus 3 squared times the height, which in this case is delta x. Part D says, what definite integral will sum the volumes of the thin slices across the full horizontal span of the cone? What is the exact value of this definite integral? So we want to now find the volume of the entire cone, and we're going to set that up with a definite integral. Now remember, our limits of integration are basically, they're spanning the x-axis, and our limits of integration kind of, we can think about them as like, where does my leftmost slice of bread start, and where does my last or rightmost slice of bread end? So looking back up at the picture, my first slice of bread, which is like maybe here, and it has some thickness to it, it starts at x equals 0. And then if I continue to draw these slices of bread, my last slice of bread would be here at x equals 5. So my limits of integration here are going to be from 0 to 5, and then the thing that we are integrating is basically this thing here, and we just have delta x changed to dx. So I have pi times negative 3/5 x plus 3 quantity squared times dx. And it does ask us to find the exact value of this definite integral. So I'm going to go ahead and I'm going to factor out pi. And I'm going to also go ahead and multiply negative 3/5 x plus 3 squared. So we get this polynomial quadratic when we expand that out. Now I want to go ahead and take my antiderivative of this polynomial. So we get 9 over 25 times x cubed over 3 minus 18 over 5 times x squared over 2 plus 9x. Luckily, our lower limit of integration is x equals 0, so we won't have to do as much calculation. All right, so I went ahead and I evaluated my antiderivative using my limits of integration, and when you simplify that, you do end up getting 15 pi. Now, part E says, compare the result of your work in part D to the volume of the cone that comes from using the formula, and likely you would have seen this formula in geometry, and so I'm just going to copy down this formula that the volume of a cone is equal to 1/3 pi r squared times h. So if you go back and you look at the picture or the earlier part of the problem, we know that the radius of our cone was 3, and we know that the height of our cone was 5. So 3 squared is 9, 9 divided by 3 is 3, and then essentially we get pi times 3 times 5, so we end up getting 15 pi. So that's kind of cool. What this shows is that we have this formula from geometry on how to calculate a volume, but we could have also calculated the volume using a definite integral and calculus. Now, it's probably much easier for us to just use the geometric formula, but we'll find in this section is that we're going to be taking the volumes of shapes that we don't have geometric formulas for, so we are required to use calculus. Example 2 says, use integration to find the formula for the volume of any cylinder. Now, that seems like a big ask, but in reality, remember a cylinder is just basically, we have two bases that are the same size, shape, and orientation, and they're parallel, and we're connecting them together basically. So really, my base shape could be anything that I want it to be. So suppose that I wanted my base to be a star, and I have another star here. My drawing is really bad, but pretend that they're the same size, shape, and orientation, and I'm now connecting all of these, and so it forms a cylinder. And so I want to find the volume of this thing, and suppose that it's just here kind of floating between x equals a and x equals b. So the volume of this shape is going to be the definite integral from a to b. And the reason that we're able to answer this question is because if I took a slice of bread, of this oddly star-shaped loaf of bread, what happens is if I slice it and I take a cross-section and I kind of just look at it, all of the cross-sections of a cylinder, regardless of where I cut it, they're all going to have the same shape, and therefore they're all going to have the same area. So another way of saying that is that going through and cutting this loaf of bread that's star-shaped, regardless of where I cut it, the area of each face or cross-section is constant. And so here, I'm just going to call this capital A to represent the area of any of my cross-sections, and I'm integrating this with respect to x. And we know from previous integration properties that the antiderivative of a constant is a times x if we're integrating with respect to x. So this is going to end up equaling a times x from x equals a to x equals b. And if I use the fundamental theorem of calculus, I can write this as capital A times b minus a. And this represents the volume of any cylinder where capital A represents the area of any cross-section between x equals a and x equals b on our cylinder.